periodic property. Goal number 4. Ionization energy. We have learnt about the atomic radii and its periodicity. Now, we turn towards another periodic property entitled as ionization energy. Let's define ionization energy. It is the amount of energy required to remove an electron from a gas atom. The ionization energy is always positive. In simple words, if you take a metal and an electron is being removed from this, we get M tends to M++ 1 electron, delta H, which is equal to IE1. This is ionization energy. Now, if one more electron is removed from this isolated gas, then we get M plus tends to M2++ IE minus delta H, which is equal to IE2. So, this is the second ionization energy. Here, the point to be noted is that the first ionization energy will be lesser than the second ionization energy, and second ionization energy is always greater than the first ionization energy. If you take an example, that is, first ionization energy of nitrogen atom is greater than the first ionization energy of oxygen atom. In this, nitrogen atomic number is 7, which is equal to 1s2, 2s2, 2p3. Here, we can notice that the s is completed, but the p orbital is half filled, and we know that as compared to the half filled, the other one, which is complete, is more stable. Since it is half filled, so it is stable. When we come to the oxygen atomic number 8, which is equal to 1s2, 2s2, 2p4, here it is partially filled. Therefore, it is unstable. When we go to the second ionization energy of oxygen is greater than second ionization energy of nitrogen. Why? Because here already one electron is removed from nitrogen. So it will be N plus, which is equal to 7 minus 1, which is equal to 6. That is 1s2, 2s2, 2p2. So it has only 2 electrons. As it is partially filled, it is unstable. Whereas for oxygen, it is 8 minus 1, which is equal to 7. Now this is half filled, so more stable. From this, it is clear that second ionization energy is always greater than the first ionization energy. It is measured in kilocalories per gram atom or in kilojoules per mole. It is also measured kilocalories per atom. The simple combination is 1 electron volt is equal to 23.06 kilocalories or 96.03 kilojoules. So the energy required to remove an electron is measured in this way. As we are discussing the changes in periodicity along the period and across the period and down the group, we also need to see the factors which determine the ionization energy. First, we'll discuss changes or variation across the period from left to right. As an atom moves across a period, the ionization energy increases because the distinguishing electron will be always added in the same orbital, due to which the extra nuclear charge will pull the electrons toward it, and there is a strong attraction between the nuclear charge and valence electron. Therefore, you need more energy to remove the electron. Furthermore, the ionization energy increases from left to right, but when we move down the group, the differentiating electron has been moved down and new shell has been added. Due to the extra energy shell, atomic size increases and the distance between nuclear and valence electron increases. Therefore, the attraction between nuclear charge and valence electron weakens or decreases. Hence, here we require very less amount of energy to remove electrons. So when we move down the group, ionization energy decreases. These are the variations in the period and down the group. Now, we list down the factors which are responsible for this. Here are the factors affecting the ionization energy. First, atomic size or atomic radii. Second, nuclear charge. Third, screening effect or shielding effect. Fourth, penetration power. Fifth, orbital. So we can say that from which orbital it is removed. And sixth, net charge on the atom. We will quickly review it. When we see atomic radii, it decreases when we move across period. Then ionization energy increases. The smaller the size of the atom, the greater the ionization energy required. Because when the size is small, the valence electrons are more closer to nucleus. Therefore, there is strong attraction between nuclear charge and valence electron. Here, we require more amount of energy to remove electrons. The size and ionization energy are inversely proportional. Hence, the larger the size, the lesser the amount of energy required. Smaller the size of atom, the greater the amount of energy required. Now, coming to the nuclear charge. Nuclear charge is directly proportional to the ionization energy, because as the nuclear charge keeps on increasing, there will be more attraction between nuclear charge and valence electron. Therefore, valence electrons are held more strongly, so we require more energy. Hence, it is directly proportional to ionization energy. Now, coming to screening effect. As we already learned, the presence of inner electrons between the nuclear and valence electrons decreases the attraction between them. This decrease in attraction is known as screening effect. More the number of inner electrons, the greater the screening effect. Therefore, the lesser energy required. Here, screening effect is inversely proportional to ionization energy. As the number of shells increases, the number of inner electrons increase. There will be more number of screening effects, and if the screening effect is more, the nuclear charge effect on the valence electrons will be less. So here, less amount of energy will be required to remove electrons. Then coming to penetration power. As we know, the s orbital will be more closer to the nucleus. So the nuclear distance between the orbitals is very important. Therefore, the order is like this. Minus s will require more ionization energy than the p orbital. P orbital requires more ionization energy than d orbital. D orbital requires more ionization energy than f orbital. So here, f orbital will be more away from the nucleus and they have less nuclear charge on valence electrons. Now coming to the next, net charge on the atom. The net charge is directly proportional to the ionization energy. Let's take an example. Al3 plus requires more ionization energy than Al2 plus, and Al2 plus requires more ionization energy than Al plus. So the greater the charge, the greater the ionization energy. Therefore, the net charge is directly proportional to ionization energy. Here, we will take one example across the period and down the group and see how the factors will be affecting. We will take the example of one group elements. We have here lithium, beryllium, boron, carbon.